Hello, everyone. My name is Crystal Shaughnessy. I am the event specialist at EDB, and I will be your host today for our webinar on Postgres and the artificial intelligence landscape. I am joined by Bruce Momjian, Vice President and Postgres Evangelist at EDB. Before I turn it over, I'd like to just review a couple of housekeeping items. Firstly, the presentation is being recorded, and we will be sharing the recording along with the slides after the broadcast. Secondly, please note that the lines are currently muted. We do expect the presentation to last most of our time today. However, we also plan to take questions at the end of each section of the presentation. So that being said, if you do have questions along the way, please feel free to submit them into the Q&A panel. If we do not have time to address all of the questions per section, we will of course follow up afterwards with any attendee whose question was not answered. So with that, I'll hand it off to Bruce.
Thank you, Crystal. Wonderful, wonderful. Thank you. Great to be doing this event for EDB webinar series. It's been a while since I've done one just myself, so it's great to be back. Again, my name is Bruce Momjian here in Philadelphia. Been EDB employee now for 15 years, and Postgres core team guy, or one of the core team guys for 25, so a long time there. This is an interesting presentation because obviously it's relating to artificial intelligence, and I'm going to try and sort of span the whole artificial intelligence landscape, as I say in the title, into this 45-minute roughly talk. If you're interested in the slides, we have a URL right here where you can download this slide deck or any of the other 57 decks that are out there. There are videos of many of these recording presentations, including this one, 90 some videos of these talks. I will also mention this is my 501st Postgres event since 1996, I guess, when I started. So somewhat of a milestone there. So it's wonderful to be speaking to you today, and I'm looking forward to it. What are we going to be talking about today? Is, again, as I said, I'm going to try and sort of get the whole landscape scrunched down into something meaningful. Obviously, I've been sort of, on the periphery of artificial intelligence way back in the 80s and 90s, where, it was sort of a big thing, and now it's a big thing again. So we're going to talk about initially what is artificial intelligence, and then we're going to talk in real detail about machine learning and deep learning, and talk about sort of what the structures are operationally, how it works, what the most popular sort of implementations are today in terms of how the process works. And then for section 3, we're going to demonstrate using Postgres. And this is going to be a pretty silly example. I'm not going to be solving any of the world's great problems with artificial intelligence today, but it's a simple problem that I think will be illustrative. And then we're going to sort of divert away from that and start to talk more practically about hardware and software, some of the challenges of actually implementing artificial intelligence. And then to wrap it all up, we'll talk about some of the more common tasks for artificial intelligence. And finally, why is a database useful for artificial intelligence? So let's get started. What is artificial intelligence? I actually got this definition from Wikipedia, which is sort of the closest I found to a good explanation. And I'm just going to read it. Machines that mimic cognitive functions that humans associate with the human mind, such as learning or problem solving. And what I take away from that primarily is a very philosophical question of whether artificial intelligence is indeed artificial. Is it mimicking how we think, or is it how we think converted into silicon, right? So what actually is happening there? And that is a very philosophical question, but I'm not going to solve it here. But I thought it was interesting to kind of probe in and understand what this sort of distinction is, because this distinction really controls exactly how useful artificial intelligence will ultimately be. This is a sort of a again, even more philosophical approach to artificial intelligence. And I think it's interesting. There's an Atlantic Monthly article there at the bottom if you're really interested in diving into this issue. But the concept is that if you only believe that the physical world exists, then human intelligence therefore must be also a physical process. And therefore, the thoughts that we have, the presentation I'm giving, your understanding of what I'm saying even now, only differs from machine intelligence because it's not naturally developed. So the concept is that if you embrace a physical world only view of humanity or intelligence, then effectively artificial intelligence is really just different in how it's created. It's not necessarily different in a fundamental way. And in fact, human free will, which we assume I'm going to pick up this cup, I'm not going to pick up this cup, is actually an illusion because it's all part of a physical process. So I don't really know how you want to go down that rabbit hole, but it really interested me to sort of think about what that means about who we are and about how we think and about what freedom we actually have to think and what our thoughts really are. So way out there, but I don't get a chance to kind of delve into this kind of stuff with computers a lot, but I think it's really interesting. The history of artificial intelligence is checkered. Uh, in the pre-computer era, artificial intelligence was considered to be something that looked like human motion or human activity. So you think of like robotics, for example, as something moving their arms. That's artificial intelligence. Then we had the Turing test, made famous by Alan Turing, where you ask questions of a machine, and if you can't tell whether it's human or not, then it must be intelligent. That's kind of an interesting concept. Expert systems, which were really big in the 80s, tried to codify the understanding of experts. They would interview experts, understand how they make decisions, and then codify that into a program or into a flow of making decisions. That ended up being much harder than you thought. Then we have AI winter, which is sort of the 90s up until I'd say the mid 2000s, where artificial intelligence really wasn't going anywhere. And frankly, I had sort of dismissed it years ago as a fusion energy, always 10 years away, which was true in the 70s when I used to talk to. I had a friend whose father was in fusion energy at Princeton, and it was always 10 years away. And then, you know, 1990, it was 10 years away, and 2000, it was 10 years away. And interesting, I just read an article today that they're making supposedly good strides in fusion energy, even the past week. So it sounds like maybe it isn't 10 years away anymore, but there's still a lot of challenges, and there's still a lot of challenges with artificial intelligence. The kind of problems that we can solve are fairly limited. I think a real sobering uh, case was Deep Blue, the IBM computer that played Jeopardy and won, and there was a lot of hype and really positive hope that artificial intelligence had finally happened and that things would change and so forth. And if you look at the popularity of Deep Blue and the IBM artificial intelligence project since then, it's been quite disappointing. In fact, to the point where IBM has sold or will be selling off their Deep Blue technology. They've tried it in a bunch of places. Particularly, they were really keen on healthcare, and for whatever reason I can't get into, it didn't work, or it hasn't been a positive experience. So very sobering. That sort of whipsawing back and forth is endemic, I would say, in the history of artificial intelligence. And the future is interesting. I don't know if it's bright, but it's definitely interesting. Artificial intelligence naming. This is a real interesting quote by Kevin Scott. uh, I love this. In a certain sense, I think artificial intelligence is a bad name for what it is we're doing. As soon as you hear the words artificial intelligence, they start making associations to their own intelligence and so forth. And they superimpose expectations on software systems. And that's basically saying that's not realistic. And again, I have some URLs at the bottom if you'd like to sort of dive in there and get some more information. But again, that's sort of I want to set up this topic because I think it is often overhyped or over expected, and I think we have to be kind of realistic of what's possible, because we do have some big successes, and I'm going to talk about those as we start to get into actual application. Another quote from Kevin Scott and another two URLs here. Um, algorithms just math, and basically you're just doing math, and they're trying to talk about how it's different than the brain and so forth. So, any questions so far, Crystal, on that? I know that it was sort of like way out in space, but I felt like I had to start at least giving a grounding of what we are talking about.
Yes, we had a couple of questions come in. The first was sort of a bundle, and the first half of it being that they were interested to know if there were any, if any, and how machine learning was used in PostgreSQL development, and second to that, how that can be applied, machine learning as a DBA to enhance supporting Postgres.
Great question, and I have a slide in section 6 for that. So that's
okay.
Great.
There you go. The second question was if you could maybe talk a little bit about the relationship between artificial intelligence and data visualization and how that relates to Postgres or Postgres extension capabilities.
Okay, yeah, that's probably section 6 question. Yeah.
Okay. Well, there we go. That's all we have for now. So we'll ask those later.
Excellent. So I know that first section is out in space. Now we're going to take it down to the ground. Okay. Artificial intelligence, again, is this huge topic. It's part of expert systems, robotics, human vision, computer vision, right? There's a whole bunch here. But I'm gonna kind of drill it down to things that are applicable, I think, to us. And there is a URL here at the bottom of a video from, I believe it's MIT. It's a 3-hour video that talks about machine learning, deep learning. I recommend that video if you're looking for sort of a primer on what this field is about, because I had to spend quite a bit of time kind of understanding what it is. So basically, artificial intelligence is this broad category. Inside the artificial intelligence is probably, I would say, the most popular and the most successful artificial intelligence applications that we've ever seen, and that is machine learning. And I'm going to talk about machine learning in the next 2 sections and go through some specific examples of how it works. And inside machine learning is a subset called deep learning. And deep learning is effectively a special use of machine learning that I'll talk about. But I want to show you this diagram so you have an understanding of kind of what we're talking about and how each one is sort of part of a larger piece here. So let's talk about machine learning basically. And this slide, I know I'm showing you like a slide that doesn't show a whole lot, but we're going to see this kind of slide over and over again. And again, we have a URL here at the bottom. If you download the slides, you can click on the URL. It'll open the URL on your browser right away. So feel free to bounce around after this talk. But this slide is really key to understanding a lot of the later slides, and I'm going to kind of walk you through it. It's basically looking at something called a tensor, and a tensor is, and I believe you can see my mouse, is basically this pink rectangle here, made up of 3 parts. So this is what we call a tensor, and we have 3 things called. Each tensor is made up of multiple neurons. Now I know the neuron term is actually from the way we think of our brains. It's somewhat of an unfortunate use of the term, but that's the technical term. The term tensor is a mathematical term. It really represents a special type of vector. But we're going to talk about tensors and neurons really in the understanding of machine learning. So a tensor is basically a bundle of neurons. In this case, it's 1, 2, 3 neurons. So this whole thing is a tensor, and we've got 1, 2, 3 neurons right there. And we basically show this tensor in 3 different states. Here's the initial state of the tensor. Here is the state of tensor during what we call training. And here is the state of the tensor when it's actively being used for artificial intelligence. Okay, so you're going to see this format of slide a lot. This is the initial state. As you can see, all the tensors are empty because we haven't done any training yet, because this is initially all blank, right? This is the training tensor, where we've actually are using training data to basically set the weights in each of the tensors. Notice I have a slash here. You can see it's going up and down. And here's the final result when it's actually ready to be used for artificial intelligence. And you can see all of the neurons have different heights to them. Okay. So again, initial tensor, training tensor, final tensor, and here is these are empty neurons. These are neurons that are being changed based on the training data, and these are the neurons with final values. Okay. And I'll be referring to this type of structure repeatedly. So the way that there are three types of machine learning, and I'm going to walk through from simplest to most complex. The most simple one is something called unsupervised learning. And there's only there's not a whole lot of use case for this, but it's the simplest one, so I just want to give it to you. Okay, so you basically create your tensor, right, with 3 neurons, all blank, and then you put your training data in with no results at all. You're just pumping data in, all right, but there's no outcome with that result. And then when you run your machine learning, your artificial intelligence here at the bottom, you're basically looking at output, and you have to make sense of the output. Because you didn't feed any results into it, you're just going to get a number out or some kind of probability of result. The only example I've ever heard of that's good of this one is you have pictures of cats and dogs, and you just put cats and dogs in, and you hope the system figures out the difference between them without any training at all. Uh, there are some use cases for this. It's not. I think the use cases are limited, frankly, because I think it's hard to interpret the results, and you better have some data that actually shows that the AI actually sort of triggers on. And again, depending on well, we get into details in a minute, but depending on what the neurons are measuring, you have a sort of direct it where it goes. But again, it's kind of a crude, I would say, machine learning example. The supervised machine learning, I think, is much more practical, and that's the example I'm going to show you in section 3. Here we have the initial state, which is all blank. Then we have the training data, and this training data has results. So this might be a true false result. It might be a fraud valid transaction result. It might be dog cat. It might be different country outputs. I mean, it could be a whole bunch of things. All right, but it has some results attached to it. And by having some results attached to it, when you finally get to the bottom stage, when you're ready to actually run the program and run the artificial intelligence, those results hopefully will match the results that you fed in, because you're basically trying to train the system with the results to say, here's something that I want to have a low value on, and here's the result, and here's something I want to have a high value on, and here's the data. And you hope the system can kind of now take new data and make the same distinction as you made with the training data. So you're trying to replicate the training data when you actually get to live data, because you probably only have historical training data or training data that you've curated yourself. What you really want is the ability, once you're done, to run the AI or the machine learning and get results with you not having to make that distinction anymore. That's really what you're kind of getting at as a machine learning goal. Reinforcement learning, very similar to machine learning, except that you have some feedback loop. So when you finally get your results, you have some mechanism to retrain or improve the machine learning or the neuron values. So if the machine guesses incorrectly or correctly, you would feed those results back to the system. If you think of the way that we do spam detection on email, very similar to that. You get an email, the system learns from your email traffic what's valid or not. But as soon as you mark an email as spam, that spam is going to go back into the system. In this case, it's spam assassin for me. It's going to go back in the system and it's going to set new keywords as being spam indicators. And every new email that comes in that's not spam is going to lower values for certain indicators. And that's sort of that feedback loop. So very rarely can you sort of set it and forget it. Almost all the machines have to have some feedback loop or a retraining process because the data is going to change over time and you want to have a system that can adapt to that. And that's really what reinforced machine learning is. I promised I was going to talk about deep learning, and this is basically deep learning. What deep learning is a connection between multiple machine learning systems. So instead of having just the first machine learning setup, you have multiple of these machines that are all hooked together. So as you can see, every neuron, its output is fed into every neuron of the next machine learning. And then every neuron of this is fed into the next machine. And again, URL there at the bottom to explain deep learning. The best example I've seen of this one is image detection, so or voice detection. So you'd have one, one that would look at distinguishing the background from the foreground, one machine, and then the next one would look at colors, and the next one would look at shapes, and the next one would look at maybe patterns or size, and you kind of work this together. Or if it's one that's trying to interpret voice, one would be sort of pitch and timing, and one would be frequency, high low frequencies, and maybe the next one would try and distinguish words between each word separate words, and the next one would try and use the words to interpret something. So you can imagine how you would cycle through some of these hard problems with simpler machine learning phases instead of trying to do the whole thing at once, which would be pretty impossible. This is a very popular way of making machine learning handle more complex problems by hooking them together effectively. Any questions so far for section 2, Crystal?
Yes, we just had one come in on slide 11 and it
Yeah.
asked, is it about running Python library into Postgres database?
I will cover the Python library options in section 4.
Okay.
Yep.
Thank you.
Because yes, this is a very popular use of Python. For section 3, I wanted to show you a very simple example of using AI with Postgres. This is not in any way production ready. Okay. What I'm going to try and do is set up machine learning so that Postgres can determine if a number has a non-leading 0 digit. All right. So if you look at the first bullet there, 31903, there is a 0 in that number, a non-leading 0 in that number. Okay. And if you take a look at the second number, there is no non-leading 0. So how would we train a machine learning to do this? Now, of course, there's much easier ways to do this. And I'm not pretending this is in any way something somebody would do, but I believe it will be illustrative. So what we're going to do is we're going to walk through an example doing it in Postgres. All right. So you can kind of see what it would look like. And what I'm hoping to do is to take what we talked about in section 2 and put bones on that, help you to see here is an actual example of us doing this process using Postgres. So I'm going to use PL Perl. I know somebody just asked about Python. Yes, I easily could have used Python here. I use Perl just because I'm more familiar with Perl, and also because Perl's a little smaller on the screen, so I can do things a little more compact and a little shorter to allow you to see what's going on. If you'd like to run this yourself, we have a URL here at the bottom, which if you click on it, will give you an SQL file that you can just run it through PSQL, and you'll just see the whole presentation, this whole section, just run through and set up an example. You can play with it yourself. So I'm going to show you a bunch of functions. These functions are effectively used to implement the AI process, you can imagine the title is functions generate tensor, and that's exactly what it's going to do. It's going to create a number of neurons, and it's going to populate those neurons. All right. So generate tensor. What I decided my tensors were going to measure are the number of digits in the number and whether the number is divisible by 10. Those were my two criteria for my tensor. So I have 11. I have 11 neurons in my tensor. Okay. The first 10 are, does this number have this many digits or more? Because the more digits a number has, the more likely it has a 0 in there, right? 2-digit number, not as likely. 9-digit number, more likely to have a 0. So I measure the number of digits in the number. And then, of course, if it's divisible by 10, then by definition, there's a 0 in the number because the first value is 0. So I basically created my tensor right here. And I basically create 10 tensors with my number. And here's my divisible by 0. And I basically output true or false, depending on my tensor values. And I return a Boolean array for this. So you might not be really familiar with Postgres, but this is a PL Perl function, which effectively does the tensor creation for me. I also need to create a training set. Remember, we talked about the training phase for our machine learning. So I've basically created a table called training set. Okay. And I generate 10,000 random numbers, and I run them through I basically generate them. This is a little, they aren't quite random. They are a random number of digits. They're not random numbers, because if you just do random numbers, almost all the digits will have 8 or 9 digits in them. Okay. So I kind of fiddled with this and I made it kind of a random length number in terms of number of digits. And then we effectively run that into our training set. We insert them into, here's our comparison for 10, and here is our generate tensor, where we basically create that Boolean array of all of our kind of numbers like that. This is basically this is the simple answer. Is there a 0 anywhere? Yeah, just do percent 0%, and you know whether there's a 0. So this line actually is our training data with results. That's our result right there. Is there a 0 in the number? If we convert the integer to text and we look for a 0 in there. Okay, so this is our training data. All right, this is what it looks like. We have a number, an integer. Is there a 0 in there, true or false? And here are the tensors with their neuron results. Okay, so you can see, for example, this one has a 0, this one doesn't. And you can see the tensor values for the various numbers. Okay. We also, in artificial intelligence, have a concept of weight. This is actually pretty important. What you're actually setting when you're doing the training is the weighting of the neurons. So the neurons start out at like 0, and we basically set the weight of how important those neurons are compared to other neurons. So some neurons may be very, very important, some not as important. And we effectively have a way of generating weight here. This is a multi-page function, so it's called generate weight. This is the body of the function, which effectively is determining how important some of these neurons are within the larger set of neurons. Okay. And then we also have to do something called balancing, where we compute the balance of the weights compared to the other weights in this set. So we have to kind of balance them all so they all equal 1, basically. So we're kind of, balancing them out, and that's what kind of does. We have something called a tensor mask, where we can mask out certain values of the tensor or not, depending on whether it's like true or false. This is pretty standard Perl function. We have the ability to sum the weights. So when we run through in production, we're going to put a number in, we're going to get a whole bunch of tensors out. We have to sum them, and then we have to do something called a soft max, where we kind of set them all to be the equal footing. So we might have, like, we don't want something to be 5 and something 10 and something 20. we want them all total to 1 or 100%, and we kind of just balance them out so they're all within that 0 to 1 range, and that's kind of what that does, softmax. And what we effectively are doing here is we create our table tensor weights true, and we're loading our training data. So here's our training set, and we're passing the SQL query into the generate weight function. Generate weight function is going to run the query on the training set for true, and it's going to load it into a table called tensor weights true, and we're going to have another table called tensor weights false to get the weights for all of our false criteria. These are the weights it came up with, the 11 weights for true and the 11 weights for false. All right. And now we're going to test it. We're actually going to, now we've got our weights, we're going to run the artificial intelligence live. We're going to put 100 through there, the number 100. And number 100, it doesn't come up with a very good estimate. It says there's a 22% chance that it's true and a 77% chance that it's false. That's not a very good, obviously it's true, and it only has a 22% chance it's true. So it didn't do very well here. For 101, it does much better. So here it's saying there's only 11% chance it's true and an 88% chance it's false, right? And the reason for the difference is that last tensor, the one that looks whether it's divisible by 10, that's true here and it's false here. And that's what changed that percentage in half, basically, because it used that last digit to say, oh, if there's not a 0 at the beginning, then wow, well, now we really are less likely, and it dropped it down significantly. Here's a bigger number. This is a long number. Unfortunately, it has no zeros in it. And the system comes out and it says, hey, 69% chance it has a 0. Didn't work too well. We can run it with more values. What I'm going to run actually is 1,000 numbers through the system. So I'm going to run 1,000 numbers through our training, our live artificial intelligence system. And I'm going to do some statistics on it, and I'm going to do some analysis on it, and this is my results. So effectively, I've run a whole bunch of numbers: 6, 61, 6180, 727, 460. All these numbers are going to run through. This is what I know it's true or false, so I can check to see whether it was accurate or not. And here are the percentages and the accuracy of how good it is. And what it's basically saying is that it was probably plus or minus 15%, and it was roughly 72% accurate in running, this particular case. Is that a great number? Not great, but it's not terrible either. So when you run a lot of numbers through, you start to get pretty good results, although we saw individual results were pretty poor in the couple we happen to do. So one of the things I think you take away from is you're not looking at certainty here. You're looking at likelihood in a lot of cases. And if the likelihood can you get into the 90, 95, 98%, then you start to get useful likelihood. Some of these numbers, 72% likely, 40% likely, that's probably not that helpful. So unless you can really get to something that is closer to certain, or either whether it's true or false, closer to certain, then you're starting to get useful. But really in this example, we kind of didn't come close, and I'm not surprised. It was a simplistic example, but what it did show was how we walked through the steps, how we created the neurons and the tensor, how we created the weights, and then how we did the training data, and then we created the weights for the training data, and then we actually ran it live. It's kind of cool. Any questions yet? Crystal probably has something.
Yes, we had 3 come in. The first came in just kind of at the start of this section,
Yep.
and it's asking, with regards to a learning process, are there equivalents to the quote utility function of happiness/economics, i.e. functions that can estimate when most of the possible learning has been reached?
That's what I didn't get into my research is there's a lot of academic and practical advice on when does learning stop, when do I need to do relearning, when does relearning hurt me, how often you can do too much relearning, for example, and then you get into it flips over. The system starts to think true is false and false is true. I unfortunately can't make comment on that because I didn't get that deep into it. But there is a lot of research on how much training data do you need to be effective. And the second big question is how important does that retraining take, and how often do you do it, and how do you make sure you don't break it while you're doing it? Those are absolutely key questions that I did not get into in my research.
Okay. The next would be, what are the unique advantages of using open source database as Postgres for artificial intelligence?
I'm going to talk about that a little later. Yeah,
Okay.
section 5 probably.
Section 5. Okay. And the last question is, can you elaborate on the untrusted about Python?
Yes. So one of the big advantages to Perl is that it has a trusted mode where the Perl is run in a sandbox. And fortunately, for Perl, they designed it that way at the beginning when they were designing the language. They had that sandbox concept. Python, I believe, did not have that concept at the beginning, and they tried to add it later, and they were pretty unsuccessful. They had a sandbox for a while. People kept finding problems with it, and they eventually abandoned the sandbox concept for Python. And because there is no trusted sandbox for Python, we can't have a trusted version of Python. For Postgres, we did have a trusted version of Python for Postgres probably in the early 2000s when Python was advertising a trusted version, a sandbox version. But they've since given up that. I don't believe current Python supports it. I'd love to see it come back, of course, but it is very hard to add a sandbox to something that wasn't designed that way. JavaScript and Java, for example, are designed as sandbox implementations because they're web focused and they were designed that way from the beginning. Python does not have that, and therefore there's no trusted version, and that's why, unfortunately, Python functions can really only be written by people with super user access or people who are granted that permission, because you can access the file system. You can go outside of the database using Python in a way that you can't with trusted Perl.
And Bruce, can you just elaborate? Someone's asking what you're referring to when you say the sandbox.
Yeah, a sandbox is effectively a way of executing code that is safe from accessing the operating system, accessing the file system, accessing networking, accessing interprocess communication. So when you're running something in a sandbox, as Java does, as JavaScript does, you are isolated. You cannot go beyond the confines of the language itself, and that is what that sandbox for Java, it's a virtual machine, but it's more than that. It's not really a virtual machine issue. It's more the protections around people who write in the language of whether they can reach outside of the language itself to interact with other parts of the operating system.
Okay, and it looks like the last question is similar to the question about elaborating on the untrusted of Python, but in regards to R.
Yes, so R, I I am not clear on R as a trusted language. I haven't used R. I know Joan Conway is our big R language person. I don't know enough about R to know whether there's a trusted version of that or not. But basically, you would find out right away because either there's a version installed or there isn't. In every case, we either, for example, with Perl, there's Perl and PL Perl U. For Python, there's only Python U. There's no PL Python. There's Python U, which is the untrusted version. So that's kind of, yeah, you would know right away. It isn't a separate code base. It's basically two modes that we operate in. And for Perl, for PL Perl, we operate in sandbox mode in Perl. And for PL Perl U, we do not operate in sandbox mode, and we can interact with the rest of the operating system.
Excellent. Looks like that's all we have for this section.
Great. So we're gonna get into much more practical parts here, which I think will interest a lot of people. One of the things I think right away when you're talking about doing artificial intelligence is, do you want to do it in the client, or for a database, do you want to do it in the server? So in the client, you can actually do all of the artificial intelligence, and therefore, if you need data from a database, you're going to bring that data down from the database to your client. And again, there's a URL here that is an example of that. And I even have a URL here at the bottom about doing that. Although I'm sorry, I mistyped that, and I'll fix that in the slides. But it has HTTP. I'm just seeing that right now. I made a boo boo. See that right there? That shouldn't be there. Bad H there. I'll fix it. But if you're doing everything client side, then you're bringing the data down. I think one of the more interesting cases for artificial intelligence is doing artificial intelligence server side. And I'm going to go into more detail in the next section about that. But you can, for example, in PL Python, or specifically PL Python U, install libraries like MATLAB, Scikit, TensorFlow, Weka. You can install those on the server side. I know that might sound counterintuitive to people, but it works. Dave Page, who's an employee at Enterprise DB, has written a bunch of blog entries about that, where you could effectively do server-side PL Python and call what you would think of as client-side artificial intelligence libraries, but use them in the server. And I think that's a really, really creative. And again, somebody was asking about open source. This is a great example where Postgres doesn't have to have artificial intelligence built in. We have PL Python. PL Python gives us all these access to all these client-side AI tools, and you have much more flexibility than us sort of trying to be better than MATLAB or trying to be better than TensorFlow. We don't have to do that. We just need to work with them. Open source makes that real easy. Madlib, another one, although I will admit that I get MATLAB and Madlib confused because they're almost spelled the same. And Scikit, of course, also can be used server side. And again, a nice URL there explaining how to do that. So again, the concept of doing server side, I think AI is really interesting. As you can imagine, this process can be very CPU intensive because you're talking about a lot of calculations, a lot of data. GPUs can be very helpful here, and there is some work being done on Postgres to improve our ability to use GPUs for server-side computations. Because as you can imagine, if you have tensors that have millions of neurons, and you're now connecting that to another layer, which also has millions of neurons, you're looking at a trillion. Hopefully, if I did the math right, a trillion connections. And deep learning again can have that kind of issue, and deep learning can have thousands of layers. All right, so imagine, it just gets really bad. So GPUs are really good for this kind of repetitive work, and you do see a lot of GPU work in AI, and there's no reason that also can't be done by Postgres. Any questions? I know it was really short, but I wanted to just kind of branch off sort of that application part.
Yes, we just had one come in.
Yeah.
Can PL/Python lib functions in the server side be called from non-Python PL languages?
Yes. Any function you define in Postgres looks like a function to Postgres. It doesn't know what language is in. It doesn't care. You're just basically calling you're basically calling an SQL level function. So we could have, for example, a PL Perl function calling a PL Python function, which then calls a PL PGSQL function. That works just fine.
Excellent. That was the only question.
Great. So let's get more practical. Again, I've sort of built this from in the sky, right? Talking about what artificial intelligence is, to talking about what machine learning is, deep learning, and then we showed an example, and now we're kind of working to much more specific. So let's talk about the tasks that AI is typically good for, machine learning is typically good for. Chess is one that has been around since I was a kid. We had little chess computers back then. We didn't have cell phones, right? We had I remember seeing like a little handheld thing that did chess. I thought it was really cool, and inside it did some computations for chess. Jeopardy was the example I gave with Deep Blue. Somewhat disappointing in terms of how it actually became practically useful. Although beating somebody in Jeopardy is really cool. Voice recognition, I think, is very common. You see it when you talk to your cell phone. Hey Siri, hey Google, uh, Alexa. They're all using that type of concept, AI, to do voice recognition. Search results, of course, use it. Recommendation engines use it. I already talked about image detection. Weather forecasting has been huge in weather forecasting for years. And you can imagine how you would set the tensors and these type of thing, inputs of the weather, these type of cloud formations, these type of weather patterns and temperatures and humidity and barometer. And you feed that in and you say, okay, what has happened in the past? Can that predict what's going to happen now? I think a great example for me has always been fraud detection. Down here at the bottom is a URL, I believe from a bank. I think it's a US bank, talking about how they use AI for fraud detection. And you would think, okay, if I'm going to do fraud detection at a bank, how would I do that? What would my tensors measure, or my neurons? What would my neurons measure? What types of things would be important for considering fraud detection? Well, it could be charge amount. It could be whether it was a swipe of a card or a chip or a pin or an online charge, which are all different. Could it be the distance from the vendor to the chargee's billing address? Somebody far away, less likely. Could it be the distance from the last chargee's charge? So if I'm getting a whole bunch of charges in Italy, I might be in Italy, right? So it can kind of figure that out. The country of the vendor, it could be the previous charges from from the vendor to the chargee. It could be frequent charges, fraudulent charges by the vendor. So again, all these things could be part of our neuron. We could basically put that in and run it through. Okay. Now the way that the way that expert systems would do it, let me back up. The way that expert systems would do it, they would talk to experts and they would say, okay, how important is the charge amount? And the person would give them some ideas. How important is the distance? How important is whether it's a swipe or an online charge? And they would write down and codify that in a program. We're not doing that. That isn't what an expert system does. What we're looking at here is is machine learning. So we're going to blindly basically get all these measurements and we're going to feed a whole bunch of data in. We're going to choose our attributes. We're going to set the neurons and we're going to throw a whole bunch of data in, some valid and some fraudulent. And the system's going to basically set the weights of each neuron based on those numbers. Then we're going to start feeding real data in and we're going to get prediction of fraudulent or not fraudulent. Okay. And we're also going to have to improve the accuracy because, as you can imagine, fraud detection changes over time. The types of frauds that come in change over time. So we're going to have some type of feedback loop. Remember, I talked about that earlier, where we're going to have to feed back incorrect and correct results into this to reset the weights of what we're doing, similar to the way we train spam detectors for email. Any questions?
Yes.
Yeah.
Just again, at the beginning of this section, can you discuss performance differences between Postgres solutions versus a native solution such as a pure Python or any language really just not inside of a database?
Sure. So historically, what I've seen, and I've been in the database industry, I guess now 31 years, 32 years. What I've seen is that when a new technology appears, whether it's full text search or JSON or AI or data warehouse, or when new technology shows up, typically it shows up as a standalone product, a standalone solution. So you have your data warehouse, you have your full text search, you have your JSON store, you have whatever, okay, your object store or whatever. Um, your artificial intelligence store could, I mean, your Internet of Things store, whatever. And you basically, they start out separate. But what happens is once the technology matures, it usually moves closer to the database and effectively it usually ends up in the database. because that's kind of where your data is. In fact, that's what section 6 is going to talk about. The concept is that normally these things start out on the periphery as we're learning where they're good, where they're bad, where we have flexibility of just throwing it away and getting a new product. But as they mature, you start to see it move closer to the data. There's a great quote, actually also by Joe Conway, where saying sometimes you want your code near your data, and sometimes you want your data near your code. And what he's basically saying is sometimes you want to take your data to the client, and sometimes you want your code. You want to bring your code to the server. And I have a blog entry about that. If you take a look, there's 600 some blog entries, but you sort of look for the title about client side and server side, you'll see it. But effectively, the performance of something running server side, Python, TensorFlow, Scikit, whatever, and something running client side, it's the same code. It's the same libraries. It's the same language. The only difference is that it's running on the database server or it's not running on the database server. So if your workflow is very data intensive and you're having to move a lot of data, then there's a lot of value to getting that code closer to the data. So you're not having to move it, right? And also, I'm going to talk about in a minute, your code can now take part in transaction semantics and be backed up and be used for actions in the database and validation of certain things that it's really hard to do client side. So there's really no difference whether you do it client or server side. It's just a question of where you want your CPU cycles to be. I guess there could be an argument that doing some stuff client side is faster because you have a dedicated machine for that and you're not bogging down your database server. Yeah, that can be a problem. You can have a case where you're doing too much on the server. You have too much AI going on, and therefore you would be better off having 100 separate machines doing AI than one database server that has to do 100 processes together. I don't see that too much. Usually the learning part takes that time, but the actual implementation once the learning is set is usually not as CPU intensive. Although, again, if we have if we're doing deep learning, then we're computing tensors to tensors, that can get very computationally heavy. But I know there's a huge amount of work being done in server side deep learning and machine learning. I hear people doing it all the time. Very popular. And I think that's just going to continue. It's part of that general flow of new technology into the database to be closer to the data and be more efficient and to take part in more business processes than being in something that sits outside. And you've seen that with data warehouse. You've seen it with full text search. You see it with JSON. You see it with all kind of the technologies are moving into the database in a lot of ways, and some of them are moving out. So it does happen, but in general, there's a lot of value. Other questions, Crystal?
Just one. By attributes, do you mean hyperparameters?
By attributes, do I mean
Hyperparameters.
I don't know. When I said attributes down here, I just meant these are the attributes. So this slide 37. When I meant attributes, I just meant attributes of attributes is a loaded word. I'm sorry, you're right. These are characteristics of transactions, characteristics of financial credit card transactions. And I'm going to basically choose which attributes of credit card transactions I'm going to measure in my neurons, and that determines how I can determine fraud.
Okay, and we actually just had one additional come in. Is keeping the data in database better than keeping it in memory for machine learning model execution?
Well, you're going to need to store the weights at some point after you learn. Normally what happens in Postgres, in pretty much all cases, there is some argument to say that what we found across all the Postgres technologies is there's a whole bunch of cases where having a custom data warehouse, a custom full text search, a custom JSON store make a lot of sense. Okay. But the bottom line is that's probably only the top 5% of your implementations. The 95% typically are better off in a easier managed workflow that can be easier updated, that's closer to the data. So yes, there are definitely cases where a custom of any data store is far superior to Postgres, but the number of actual applications that need that custom data store and would benefit from them is surprisingly small. And I can't comment on exactly what that would make sense for that particular user, but yeah, there are cases when a custom AI is going to be faster than trying to do it in Postgres server side. There's no question. But the question is, because every time you pull something out of the database, every time you have a separate data store, every time you try and coordinate stuff together, it gets complicated. Backup becomes complicated. Transaction control becomes complicated. So it's not that it's wrong, it just adds complexity. Very similar to microservices. I'm working on a microservice talk. Same issue. Microservices are complicated. It has advantages, absolutely has advantages. But does splitting up the database to do microservices make sense? Sometimes it does, sometimes it doesn't. Very almost similar case with AI, full text search, data warehouse, across the board. It's really a question of how data intensive is what you're doing and can it be done in the database. And if it can, it usually is. It's more flexible often in the database, because what happens is a lot of these other separate products is they become very stiff and rigid because they're not flexible enough to sort of handle the new data needs of the organization, and they just sort of sit out there and do their thing, and then eventually they go away. Whereas usually doing stuff in the database has a lot of flexibility because it's a flexible tool chain. You're really close to the data. You can modify it really quickly in a way that you can't when it's sitting in a very rigid API in a separate tool. So, okay, so let me just finish up. I think the big question is, and we've already kind of pushed on this: why use a database? Why not use a separate AI tool? Right? As I said before, there's absolutely advantages to using a separate AI tool. However, that there are some advantages to bringing that AI into the database. First, machine learning requires a lot of data, and your data is already in your database in most cases. When we're talking about fraud control, we already probably have all the fraudulent transactions we need in the database to train the database with, to train the machine learning with. And also, if it's not in the database, then you got to take it out, and then you have to do something else to it. Not that it's wrong, it's just an extra step. But there are some unique values to having it in. You can use previous activity as training data right away, so it makes it really easily. You have seamless access to your data because the AI and the machine learning and the database data is in the same place. You can take immediate action on AI results. This is pretty tricky to do outside the database. You can basically say, okay, should I commit this transaction if it's likely to be non-fraudulent? Well, I can run a machine learning and get a probability of fraudulence before I commit a transaction, right? That is where AI kind of melds with the actual transaction semantics that I'm probably already doing in a relational system. Obviously, I want to have concurrency, so I get a concurrent view of my data. I'm not looking at stale data. I back it up as a single thing. And also, I can use some of the tools that are already in Postgres. I can use complex data types. I can use full text search as part of my neurons. I can use GIS location as part of my neurons. That's pretty cool, right? I can use complex indexing, and I can also use GPU to do that. So again, it's not just the data itself, it's a lot of the tooling around the data that can be really useful when you're trying to create these neurons for machine learning. And I'm just using fraudulent transactions as an example, but there's a whole bunch of other ones. Okay. So the question we had earlier, not only can we use AI in applications, but we can also improve the database with AI. We can use it for optimizer plans. We can use it for index recommendations. We can use it for database settings. We can use it for resource usage. Okay, we can use it for alerting for malicious activity and even resource exhaustion. I will say this is probably a new area. I don't think we really have a good sense of what is possible here. I know Dave Page is working on some auto tuning capability, which uses a little bit of this. So I think the future is bright for this. I think we have a lot more to do, frankly, in using AI, not only in applications, but using them to improve the database itself. This is what the question from early on was. So I want to thank you. I know our hour is up. Do we have any questions, Crystal, before we finish off?
We do not. So as you said, we're at the top of the hour. So thank you, Bruce. Thank you for everybody who joined us for the webinar and who submitted a question. As I mentioned earlier, we'll be sharing both the recording and the slides with you as soon as possible. So we hope you have a great day.